Hello children. Now we do the chapter Thermal Properties of Matter for quick revision. This chapter we begin with concept of heat and temperature. Temperature is the degree of hotness or coldness of a body which can determine the direction of heat flow. Heat is a form of energy which causes in us sensation of hotness or warmth. Heat energy can be measured using calorimeter, but temperature measured using thermometer. Heat is a scalar. Temperature is also a scalar. But heat energy is the energy which is in transit. It can only flow. The direction of which is given by temperature difference. Heat energy can only flow from higher temperature to lower temperature in the absence of external aid. But in the presence of external agencies, heat energy can be made to flow from low temperature to high temperature as in a refrigerator. In a refrigerator, heat energy flows from low temperature part to high temperature part. From inside of the refrigerator to outside of the refrigerator, heat energy flows because only there is external agency. Now, different thermometric scales. Different thermometric scales. The basic thermometric scales are degree Celsius, degree Fahrenheit, and Kelvin scales. Comparison of all these scales with that an unnamed thermometric scale. Here, if you choose a thermometric scale like this, that can be compared with other thermometric scales in different graduations. For example, in degree Celsius thermometer, the lower fixed point is chosen as 0 and upper fixed point is chosen as 100, where 0 stands for 0 degrees Celsius, melting point of ice at sea level. 100 stands for 100 degrees Celsius, boiling point of water at sea level. Now, in degree Fahrenheit thermometer, 32 degree is chosen as the melting point of ice and 212 degree is the boiling point of water. In Celsius thermometer, 0 degrees Celsius, and in Kelvin temperature, it is 273 Kelvin, 273.15. Also writing that 15 Kelvin as chosen as 0 degrees Celsius. Here it should be 373.15 Kelvin. You may have an unknown thermometer whose lower fixed point is LFP and upper fixed point is UFP. You may have reading here, some reading in that unknown thermometer. Here the reading is in Kelvin. Here that corresponding reading is in Fahrenheit and the corresponding reading in Celsius is C. How to compare all these scales? That is an important question. Reading minus lower fixed point divided by upper fixed point minus lower fixed point is a constant for any such thermometers. For Celsius scale, it should be C minus 0 divided by 100 minus 0. For Fahrenheit, it should be F minus 32 divided by 212 minus 32, and for Kelvin, it should be K minus 273, I'm neglecting 0.15, divided by 373 minus 273. Then writing it once again, C by 100 equals F minus 32 by 180 equal to K minus 273 by 100. So this comparison is very important, among which you can compare Celsius and Kelvin alone. Celsius equal to K minus 273, so Kelvin is equal to C plus 273. For example, if C is equal to 27 degrees Celsius, then K is equal to 300 Kelvin, so and so. Similar comparison can be made by using Celsius and Fahrenheit. You can write as C by 5 is equal to F minus 32 by 9. This also is very important. So comparison of thermometric scales. From these pictures and all explanations, you may have come clear that Fahrenheit thermometer is more sensitive because unit degree rise of temperature in Celsius scale is corresponding to 1.8 degree rise in temperature in Fahrenheit scale, because in Celsius thermometer 100 equal divisions, while in Fahrenheit thermometer there are 180 divisions. Okay, then 100 divisions correspond to 180 divisions. That means one division correspond to 1.8 degree divisions in Fahrenheit. So unit degree rise in temperature in Celsius scale is corresponding to unit degree rise in temperature in Fahrenheit. Sorry, 1.8 degrees Celsius rise in temperature in Fahrenheit scale. At the same time, unit degree rise in temperature in Kelvin scale. So 1 degree Celsius rise noticed in Celsius scale is equivalent to 1 Kelvin rise in Kelvin scale. So Celsius scale and Kelvin scale both are having same accuracy, but Fahrenheit scale is more precise. That is thermometric scales. Celsius, Fahrenheit and Kelvin thermometric scales. Okay, now we have to discuss expansions of solids, thermal expansion in solids, liquids and gases. Thermal expansion in solids. If the solid is in the form of length or a wire, on heating, it expands thermally. Delta L is equal to L into delta T into a proportionality constant called alpha, called linear expansivity. So alpha is equal to delta L by L delta T. Delta L is the change in length, L is the original length, delta T is the change in temperature. Unit of alpha is per degree Celsius or per Kelvin. Alpha is thermal expansivity. It can be defined as the fractional change in length for unit degree change of temperature. Fractional change in length for unit degree change of temperature. That is called alpha. So alpha refers to the fractional or percentage change in length for unit degree temperature changes. Okay, alpha is greatest for solids. Among solids, it is largest for metals. Among metals, it is largest for aluminium. Alpha aluminium is largest. That's thermal expansion in solids. For this thermal expansion provisions, only rail tracks are given small gaps. The pavements, concrete pavements are given small gaps and filled with sand. All this are a few of the examples of this thermal expansion. Also, bimetallic strip is a compound strip of two dissimilar metals having different expansivities. For example, brass and invar. Brass has high expansivity. Invar has almost no expansivity. Invar has come from the term invariant, iron nickel old form. This alloy, invar. Okay, invariant for all temperature changes. So brass invar bimetallic strip on heating would bend. It would not expand linear wise. It expands sidewise. So it expands. Why? It bends because of the uneven expansivities. Brass expands more, invar expands less. So brass will come at the outer end, invar comes at the inner end. Brass invar bimetallic strip can bend on heating. Okay, that's thermal expansion in solids. Another one, a simple pendulum having metallic rod as the suspension rod. At higher temperature, that metallic rod expands. When length of the pendulum increases, the time period increases, the watch or that clock goes slow. That happens if that is uncompensated. But normally, such mechanical pendulums are compensated for this change in length for varying climatic conditions. Okay. Next one, if the solid is in the form of a sheet, it has length and breadth, that means it has area. Then also it expands. It expands both lengthwise as well as breadthwise. So its area expands. Therefore, delta A equal to A beta delta T, where beta sometimes called alpha A, alpha L sometimes called alpha, alpha A sometimes called beta. then beta or alpha A is equal to what? Delta A divided by A delta T. Okay, of the same kind, if volumetrically that solid expands, that may be gamma or alpha V. Therefore, gamma or alpha V equal to delta V divided by V delta T. So, alpha, beta, gamma. For isotropic solids, that means if the solids have same properties in all the directions, x direction, y direction, and z direction, the rate of expansions are same, then alpha x equal to alpha y equal to alpha z, then we can say gamma equal to 3 alpha. Then we can say beta equal to 2 alpha. So gamma by beta is equal to 3 by 2. So gamma is 3 alpha and beta is 2 alpha. That's all about expansivities of solids, thermal expansion in solids. Okay, when a solid rod is pressed tightly fixed against two rigid walls and heated, there is a chance of bending. If you prevent it from bending also, there is a stress developed inside called thermal stress. We have already learned in previous chapter regarding thermal stress. Students, you remember, hope that you remember the formula for thermal stress. Thermal stress is equal to Young's modulus into Y alpha linear expansivity of the rod into delta T, Y alpha delta T, and thermal strain is equal to alpha delta T. These are both things we have revised already in previous chapters. Now, thermal expansion in liquids. A liquid cannot be heated directly. It can be heated through a solid because it doesn't have definite shape. You can take that liquid in a container and heat that container from the bottom. Then container takes up that heat, then liquid has not taken up heat, so container expands, then the level of liquid comes down. But soon after that, through the mode of conduction, heat is transferred from the vessel, conducting vessel to the liquid. So liquid start to expand, then only liquid takes up heat. Then the rate of expansion of liquid is much more than that of solid, level increases normally. So what we have to see is that there should be an apparent expansivity. The real expansivity of that liquid can never be measured directly. Apparent expansivity of liquid is equal to real expansivity minus expansivity of the container. If real expansivity of the liquid is equal to the expansivity of the container, the observed expansivity becomes 0. That means you will not notice that liquid changes its level. The liquid will stay back. When you heat the container, the level of liquid remains same. It seems as if the real expansivity of the liquid and expansivity of the container are same. But if that liquid is found to increase its level or if the liquid is found to overflow on heating, it is sure that real expansivity of the liquid is larger. But if its level falls, real expansivity is less. So the concept of apparent expansivity is worth noted in expansion of liquids. Then while we learn expansion of liquid, it is compulsory to learn about anomalous expansion of water. What do you mean by anomalous property of water? If you plot volume of fixed amount of water against temperature in degree Celsius, volume may be in meter cube, temperature in degree Celsius, you have a graph showing a variation like this, and the volume of water decreases as it is heated from 0 degree up to 4 degrees Celsius. 0 degree to 4 degrees Celsius, its volume reduces, and at 4 degrees Celsius, its volume becomes a minimum. Then that density correspondingly becomes maximum. Now, after 4 degrees Celsius, volume increases, density decreases. So water has highest density at 4 degrees Celsius. This property of water, unique property of water is called anomalous expansion. So one temperature anomalous expansion is shown by water. You can see from this graph, when temperature is decreased from 4 degrees Celsius to 0 degrees Celsius, when temperature decreases from 4 degrees Celsius to 0 degrees Celsius, volume increases. That is called anomalous expansion. Water cooled from 4 degree to 0 degree, water expands. That is called anomalous expansion. When water heated from 0 degree to 4 degrees Celsius, volume decreases. That is anomalous contraction. Don't forget, 4 degree to 0 degree Celsius, when water is cooled, water expands irrespective of whether it is heated or cooled. 4 ഡിഗ്രി സെൽഷ്യസിലുള്ള വെള്ളത്തെ ചൂടാക്കിയാലും തണുപ്പിച്ചാലും അത് എക്സ്പാൻഡ് ചെയ്യുകയുള്ളൂ. ബിക്കോസ് അറ്റ് 4 ഡിഗ്രി സെൽഷ്യസ് വാട്ടർ ഹാസ് minimum volume and maximum density. This property is called anomalous property of water, anomalous expansion. There are many natural consequences. This is the reason by which aquatic animals can survive in cold countries. This is the reason by which water pipes tightly turned burst in winter. പൈപ്പ് വെള്ളമുള്ള പൈപ്പ് തണുപ്പ് കാലത്ത് ടൈറ്റായിട്ട് അടച്ചു വെച്ചാൽ അത് തണുക്കും തോറും എക്സ്പാൻഡ് ചെയ്യുകയും 4 ഡിഗ്രിയിൽ നിന്ന് 0 ഡിഗ്രിയിലേക്ക് എത്തുമ്പോഴേക്കും അത് എക്സ്പാൻഡ് ചെയ്യും. 0 ഡിഗ്രി സെൽഷ്യസ് വാട്ടറിൽ നിന്ന് 0 ഡിഗ്രി സെൽഷ്യസ് ഐസിലേക്ക് വരുമ്പോഴേക്കും അത് വീണ്ടും എക്സ്പാൻഡ് ചെയ്യും. ഇഫ് യു ഗോ ഫോർ ദിസ് ഗ്രാഫ് further, you will notice a slight rise here. Then it goes like this. That means from negative temperature to 0 degree Celsius, ice expands. But ice has reformed at 0 degree Celsius. Now, in changing 0 degree Celsius ice to 0 degree Celsius water, again volume decreases. That is why when ice is formed from water, ice is expanded. That expanded ice in cold countries exerts pressure in water pump and bursts. That is a natural consequence. Okay. That's anomalous expansion. Okay. Expansion of liquid is also important. Okay. Then the third one is expansion of gases. Ideal gas equation. We have learned ideal gas equation PV equal to mu RT, where P is the pressure of mu moles of ideal gas and V is the volume of mu moles of ideal gas. When you take the derivative at constant pressure, P into dV equal to mu R dt, and writing P as mu R T divided by V. So P can be written as mu RT by V. dV equal to mu R dt. So mu R gets cancelled. You can also write dV by V dt as to be 1 by T. This is called volume expansivity of ideal gas. So volume expansivity of ideal gas is 1 by T, where T is the Kelvin temperature. Similarly, pressure expansivity is dP by P dt. That is also 1 by T. Volume expansivity of ideal gas is 1 by T, and pressure expansivity of ideal gas is also 1 by T. These are equal. So pressure expansivity and volume expansivity of ideal gas are same. Okay, that's very important. Pressure expansivity of ideal gas is equal to the volume expansivity of ideal gas. Okay, keep it noted. Pressure expansivity of ideal gas is 1 by T. So what is the graph showing the variation of volume expansivity and temperature? Rectangular hyperbola. Pressure expansivity and temperature, rectangular hyperbola. What is the ratio of pressure expansivity of ideal gas and volume expansivity of ideal gas? 1:1. Because they are equal. What is that? 1 by T. T is the Kelvin temperature. It's very important. By heart this. Okay. Expansion of gases. All gases expand on heating and contract on cooling. All gases expand on heating. When heat is supplied to the gas, it is used for expanding. Some part of that gas is used for expanding. Some part is used for increasing internal energy from first law of thermodynamics. Delta Q equals delta U plus delta W. If you try to heat in a vessel which is rigid container, means volume cannot be changed, then there is no volumetric changes. Then the heat supplied is only used for increasing the internal energy. Okay. Then delta Q equal to delta U. If entire heat supplied is used for increasing internal energy at constant volume. At constant volume, we know pressure varies directly with temperature. At constant volume, when temperature increases, pressure also proportionately increases. All these are very important things over expansion of gases. We have to go through all this in detail in the next chapter, thermodynamics. Okay, we'll be doing that there. Okay, now we'll be moving to calorimetry. The topic calorimetry. The heat lost by hot body. Heat lost by hot body is equal to the heat gained by cold body. Heat lost by hot body equals heat gained by cold body when hot body and cold body are in thermal contact with each other, provided no heat loss or gain from surroundings. This is the principle of calorimetry. Method of mixtures. Also called method of mixtures. Okay, when 10 gram of ice at 0 degree Celsius is mixed with 10 gram of water at 80 degrees Celsius. Water is at 80 degrees Celsius. Both equal masses, 10 gram, 10 gram. But ice is at 0 degrees Celsius. What is the mixer temperature after a long time? Okay, you can see that after a long time you wait, that entire 10 gram of ice just melts. At the end of that journey, entire mass of ice melts. So total mass of water contained in the vessel will be 10 gram ice melted into water plus already 10 gram water, hot water. So 20 gram. And the mixer temperature would be 0 degrees Celsius. You can study this example as a reference. Okay, and the mixer temperature is also 0 degrees Celsius. Complete melting has occurred. No amount of ice is left. But if the temperature of hot water was less than 80 degrees Celsius, remember, when temperature of that hot water of equal mass as that of ice is less than 80 degrees Celsius, some amount of ice would have been left behind. That means the melting is not completed. That means melting is not over. During melting, the temperature should be constant, and that is the equilibrium temperature, melting point of ice. That is 0 degrees Celsius. Okay. Now the mixer temperature is 0 degrees Celsius, but at the same time, if the temperature of the hot water is more than 80 degrees Celsius, the mixer temperature would be greater than 0 degrees Celsius because entire ice would have been melted that time. Okay, this type of problems are answered by using this formula. And this formula, you should know two things. One is the amount of heat energy required to change temperature without any change in state. That is mass into specific heat capacity into delta T. The amount of heat energy required to change the temperature without changing the state is ms delta T, where S is the specific heat capacity. At least you by heart the specific heat capacity of water, and that is 1 calorie per gram per degree Celsius. Okay. Now, specific heat capacity of ice, that is exactly half this, 0.5 calorie per gram per degree Celsius. Okay. Now, one more formula. Heat energy required to change the state of a body without changing the temperature, where it is ml, where m is the mass of the body, L is the specific latent heat of the body. Specific latent heat is of two types because there are two changes of states. Specific latent heat of fusion, specific latent heat of vaporization. Specific latent heat of fusion of ice is to be by heard 80 calorie per gram. Unit ശ്രദ്ധിക്കുക calorie per gram. Specific latent heat of vaporization of steam is much larger, that is 540 calorie per gram. Steam causes more burns at 100 degrees Celsius than water at 100 degrees Celsius because it carries latent heat. Every 1 gram of steam possesses 540 calorie energy extra than that of the corresponding one at 100 degrees Celsius. Okay, water at 100 degrees Celsius, 540. So try to by heart all this. Delta Q equal to ml. M is the mass, L is the specific latent heat. Okay, these two formula are essential for that. What amount of heat energy is used for melting? ml. What amount of use for increasing temperature? ms delta T. Okay, this is used for solids as well as liquids. For gases, little more things are to be learned. Okay, for gases, this formula will be learning in next chapters. Then, we are discussing principle of calorimetry. Heat lost by hot body equal to heat gained by cold body. It's important to note about thermal capacity. Thermal capacity. Thermal capacity, letter capital S is used. Capital S is given by delta Q divided by delta T and its unit is joule per Kelvin. Thermal capacity joule per Kelvin, delta Q by delta T. Specific heat capacity, small s is equal to thermal capacity per unit mass. Okay, thermal capacity per unit mass. So thermal capacity equal to mass times specific heat. So formula for thermal capacity, important. Formula for thermal capacity equal to mass multiplied by specific heat capacity. So thermal capacity equal to mass into specific heat capacity. Unit of thermal capacity is joule per Kelvin. Unit of specific heat capacity is joule per kilogram per Kelvin. Okay, if you choose for molar specific heat capacity, molar specific heat capacity is 1 by mu times delta Q by delta T. Its unit is joule per mole per Kelvin. That is delta Q equal to mu C delta T. The gas can undergo two distinct processes, either pressure constant or volume constant. These two different processes, gas has got two principal specific heats. One is called Cp, other is called Cv. Cp is equal to 1 by mu delta Q by delta T at constant pressure. Cv is called 1 by mu delta Q by delta T at constant volume. Okay, where delta Q is equal to delta U plus delta W, or delta Q equal to delta U plus P delta V. Now, delta Q by delta T at constant pressure is equal to delta U by delta T plus P delta V by delta T at constant pressure. Here also suffix you can keep pressure. Delta Q by delta T at constant volume equal to delta U by delta T at constant volume plus P delta V by delta T at constant volume becomes 0. At constant volume delta V is 0. Also you can omit these suffixes because internal energy of ideal gas, we are telling about gases. Internal energy of ideal gases only depends on temperature. Internal energy per mole for monatomic gases only depends on pressure and volume. It does not depend on pressure and volume, it only depends on temperature. That's why delta Q by delta T at constant pressure can be written as this. Delta Q by delta T at constant volume can be written like this. Okay, from this we can the formula for Cp and Cv, and delta Q is equal to mu Cp delta T, but delta U equal to mu Cv delta T. Okay, gas can undergo different processes also where pressure over volume is not constant. There we use the general formula delta Q equal to mu C delta T and all. Okay, mostly gas is experimented at either constant pressure or constant volume. So there are two principal specific heats for ideal gases. A specific heat can be positive, it can be negative, it can be sometimes zero, it can have any values. Ideal gas can have any values for specific heat. When in a process delta Q equal to 0, when in a process delta Q equal to 0, specific heat becomes 0. For adiabatic process where there is no heat transfer, specific heat is 0. For isothermal process where delta T is 0, specific heat becomes infinity. Specific heat of isothermal process is infinity because there is no change of state. This specific heat can be positive, it can be negative. Also, it can have any values for ideal gases. Okay. Now, what do we mean by this change of state? Change of state is the change from solid to liquid, maybe from liquid to gas, maybe from solid to gas, sublimation. Solid to liquid is melting, liquid to gas is vaporization, solid to gas is sublimation. The temperature at which state changes is called melting point. Melting point of ice at sea level is 0 degrees Celsius. And on increasing the pressure at the surface of ice, the melting point of ice reduces. That means ice melts earlier. Suppose ice is at minus 20 degrees Celsius. A huge ice block is there at minus 20 degrees Celsius. You pressurize over it, then ice starts melting at a temperature minus 20 degrees Celsius itself, even before reaching 0 degrees Celsius. But soon at the release of the pressure, it re-solidifies. This process of melting at a lower temperature and re-solidifying at the release of the pressure is called regulation. Regulation is very important, due to which glacier formed slides down to sea and floats in sea. Glacier, maybe huge ice mountains can slide. A mountain can slide, ice mountain slides, and ice mountains may be moving in land and sliding over a mountain, and it may reach sea and it may float there. This is due to regulation. Ice block you can cut by using a iron string, but after cutting that iron string moves down, but the ice slab keeps as it is. It's not broken into two pieces. It's also regulation. A person can enjoy ballet dancing. Ballet dancing is a Russian dance only because of this regulation. Splash sound is heard while walking on ice with the shoes. This is due to regulation. Avalanche is noticed, natural phenomenon, avalanche. Small ice granules happen to fall down from the top of mountain. As it coming down, it grows in size. So ice granules, small bits of ice, becomes bigger in size gradually as it comes down due to regulation. All these are natural consequences of regulation. Similarly, another change of state is called boiling. Boiling occurs when liquid state changes into gaseous state. Again, temperature is a constant. Okay, boiling point also has got a certain effect with pressure. Increasing the pressure at surface of liquid, its boiling point increases. That happens in pressure cooker. A pressure cooker can be used for fast cooking because at the surface of water, when pressure is increased, it boils at greater temperatures so that it can be cooked very well within a short span of time, even if its cooking temperature of the material is much larger than boiling point of water at sea level. Suppose boiling point of water is 80 degrees Celsius at some place, maybe in a mountain. There, normal cooking is not preferred because cooking temperature of some of the edible materials may be 100, but boiling occurs at even less than that 80 degrees. So cooking does not happen. For that, we need to use pressure cooker. So that's the advantage of pressure cooker in hill stations. It can be used for cooking at a temperature greater than 100 degree Celsius. So when pressure is increased at the surface of water, its boiling point increases. On pressurized, melting point of ice decreases. These things are to be noted in calorimetry. Okay. Now we have to move on to the next topic, mode of energy transfer. There are three basic modes of transfer of energy. One is called conduction. Conduction needs conductor. That means materials should be conducting. All metals are good thermal and electric conductors. Here we learn about thermal conductivity. If you have a metallic slab of this form, metallic slab like this, whose length is L and the ends are maintained at a temperature difference. One end is TH, other end is TC. TH is greater than TC, heat energy starts to flow from hot end to cold end. The rate of transfer of heat delta Q by delta T along the length L, cross-sectional area A, is equal to a proportionality constant into area of cross-section into delta T divided by L, Ka delta T by L. This formula is only used when after this temperature difference is established, wait for a long time. In steady state, you can use delta Q by delta T means rate of heat flow, rate of heat flow, current, rate of heat flow. Heat current is equal to Ka delta T by L. This formula is important, where K is a proportionality constant called thermal conductivity or coefficient of thermal conductivity. Let us see what is its unit. Here, energy per time is power, watts. So, watt per meter per Kelvin will be the units. Watt per meter per Kelvin. Watt per meter per Kelvin. Watt means what? Dimensionally. M L square T raised to minus 3 by L by K. That is MLT minus 3 K minus 1 and is a scalar. Dimensions is to be noted. Okay, here Ka delta T by L. This delta T by L is called temperature gradient. Temperature gradient. Delta T by L is called temperature gradient. So delta Q by delta T equal to Ka into temperature gradient. Delta T by L is called temperature gradient. Once again writing its differential equation dQ by dt equal to Ka dt by dx. Okay, like this it can be written, or as earlier, Q by T equal to Ka delta T by L. Here we can rearrange it to be like this: Q by T equal to delta T divided by L by Ka. It's of the form Ohm's law. Current is equal to potential difference by resistance, where L by Ka can be termed as resistance called thermal resistance. L by Ka is the thermal resistance. Thermal resistance proportional to length, proportional to 1 by area, proportional to 1 by K. It very much resembles electrical resistance. What is electrical resistance? L divided by sigma A or rho L by A. All this both same. All metals are good conductors of electricity as well as heat, can be explained by using this one. So thermal conductivity in solids that we are discussing. Different solids are having different thermal conductivities. Copper is best conductor. Silver is best of among metals. Then comes copper. Okay, like that steel and aluminium both have come there, but steel is best conductor than aluminium. Thermal conductivity of steel is greater than that of aluminium. So, like that questions may be asked. Silver is best conductor. Then copper comes. Okay, now if two such thermally conducting slabs are having same length, same area, but made up of different materials. One is of thermal conductivity K1 and the other is of K2. And both the ends are maintained at a temperature difference T1 and T2. Heat energy flows like this. Heat per second will be same at every second. Amount of heat flowing is constant because they are in series. In series, heat per second is constant. In series, heat per second is a constant. Now, in this, we may have been asked about the temperature of the interface. So, as heat is a constant, K1 A T1 minus T divided by L, length same, equal to K2 A T minus T2 divided by L can be used for solving this. A and L gets cancelled. Then you get K1 T1 minus K1T equal to K2T minus K2 T2. So T taken as common. So T is equal to K1 T1 plus K2 T2 divided by K1 plus K2 can be used for finding the temperature of the junction. Also, there can be one more question. What is the equivalent conductivity? Here, two resistances are to be connected in series. As in electricity, we have learned R is equal to R1 plus R2. R is equal to R1 plus R2. R1 is L by K1A. R2 L by K2A. And R is 2L. Total length L plus L 2L divided by K equivalent into A. A has not changed the same area. L by A cancel. You can write 2 by K equal to 1 by K1 plus 1 by K2. Any number of rods you can practice. 3 by K equal to 1 by K1 plus 1 by K2 plus 1 by K3. K equivalent here K equivalent equal to 2 K1 K2 by K1 plus K2. That is called harmonic mean of K1 and K2. So slabs in series, temperature of the junction as well as equivalent conductivity. Now, if slabs are in parallel, side by side, both the slabs are kept side by side. Here temperature T1, temperature T2, then rate of heat will be different H1 by T. Through the other one it is H2 by T. As they are in parallel, you can use 1 by R is equal to 1 by R1 plus 1 by R2. 1 by R1 is L by K1A, R2 L by K2A, 1 by R, L by K equivalent into area. This time area becomes A plus A 2A, but length same. So A and L here also gets cancelled. You get K is equal to K1 plus K2 by 2. That is arithmetic mean of K1 and K2. In parallel, equivalent conductivity is arithmetic mean. In series, equivalent conductivity is harmonic mean. Okay, this type of questions may be asked, and because it forms solved exercise in NCERT. Okay, that's all about thermal conduction. Okay, conduction based questions may be asked. The next type is of energy transfer is convection. Convection is made possible in liquids and gases. It is not possible in solids. Conduction is possible in solids, liquids and gases. But solids are best conductors than liquids and gases. Thermal conductivity is largest for solids because atomic spacing is less. This energy flows as heat waves. Okay, then convection. Hot air rises up, cold air sinks down. Ventilators are seen at the top of a room. land breeze, sea breeze, all these are examples, and no mathematical questions can be expected because nothing there mathematically to deal with. The third one is radiation. That's most important. Radiation. Radiation. In radiation topic, we have to learn three basic laws. First one is Stephan's law. Stephan's law of black body radiation. Stephan's law states that energy radiated per unit area per time is equal to E sigma T raised to 4. Let us see what all are that data. Sigma stands for Stephan's constant, 5.67 into 10 power minus 8 watt per meter square per Kelvin raised to 4 unit. Say scalar. E stands for energy, A surface area, T time. Small letter E called emissivity. For a black body, emissivity is chosen as 1. Okay, a black body can absorb all those wavelengths falling on it, and it can re-radiate all those wavelengths absorbed by it. That is emissivity 1. Okay, ideal black body, emissivity 1. Okay, but a white body, if it is an ideal white body, emissivity is to be 0. And if emissivity between 0 and 1, that body is called gray body. Emissivity may be 0.7. Emissivity lies between 0 and 1, that is 0.7, 0.3, 0.2, like that. That is called a gray body. Emissivity 1 means black body. Okay, mostly in our papers, black body may be asked. Emissivity 1. Sigma Stephan's constant, and it's a fourth power law. Energy proportional to T raised to 4. Energy proportional to A T raised to 4. If area different, that also may be used. Energy proportional to surface area of a sphere, R square. So R square T raised to 4. These all are asked frequently in examinations. That's Stephan's law. Okay. Next one is Wien's law, Wien's displacement law. It states that lambda m proportional to 1 by t, lambda m is equal to a constant by t, or lambda m into t equal to a constant called Wien's constant. The value 2.9 into 10 power minus 3 unit meter Kelvin. Wien's constant unit meter Kelvin. So dimension Lk, K for Kelvin, M for meter, L. Wien's law. It states that lambda m corresponding to 1 by t. What is lambda m? Lambda m is the wavelength of the radiation emitted for the energized spectral light. At a particular temperature, suppose a black body is radiating. It radiates out almost all the wavelengths that it has absorbed. If it is emitting all the wavelengths, emissivity is 1. Okay. And the wavelength corresponding to the energized radiation that it radiates, that wavelength varies inversely with temperature. That's why as temperature increases, lambda m decreases. If you go for a graph showing the variation of wavelength and energy and wavelength, you get a graph of this shape. And here energy is maximum. Corresponding wavelength is called lambda m. Let this temperature be T1. If you do that experiment at a greater temperature T2 greater than T1, you may have noticed two very important changes. One among them is the peak has shifted up. Why peak has shifted up? Because T2 greater than T1. When T2 greater than T1, E proportional to T raised to 4, fourth power. So there's lots of changes. Energy proportional to T raised to 4. Small change in energy causes, small change in temperature causes a big change in energy. So that Y direction shift will be noticeable and much larger. Okay, graph is not scaled, only schematic. Now, one more shift is noted here. That peak has been shifted to the left side. That is called Wien's shift. Because when temperature increased, energy increased, but that wavelength decreased. That is called Wien's shift. The Y shift is called Stephan's shift. X shift is called Wien's shift. So lambda T equal to B. That's important. Wien's law. Okay, now Newton's law. Newton's law only applicable for small temperature changes between hot body and its surroundings. If the hot body radiates energy delta Q divided by delta T, that is measured as product of a constant K and delta T. This is Newton's law. Rate of heat is equal to K delta T. Delta Q by delta T equal to K delta T, or its differential form dQ by dt equal to K into T2 minus T1, where T1 is the temperature of surroundings and T2 is the temperature of the hot body. Hot body releases heat. You can keep this as a reference. But already we know the heat lost can be measured in terms of its mass specific heat and falling temperature. So dQ can be written as ms dt2, where dt2 is the falling temperature of the hot body on release of heat. So the rate is dQ by dt equal to ms dt2 by dt. Okay. As it emits heat, heat energy is emitted, temperature falls. So you put a minus sign there. So you can put a minus sign here also. Then minus ms dt2 by dt equal to K into T2 minus T1. This equation is also very important. Not this equation also. Okay, from this you can rearrange dt2 divided by T2 minus T1 equal to minus K by ms into dt. Now it is integrable. You can also write log T2 minus T1 equal to minus K by ms plus C. That is T2 minus T1 equal to e raised to minus K by ms plus C. That implies e raised to minus K by ms into e raised to C. That implies T2 equal to T1 plus e raised to minus K by ms into e raised to C. This equation is also important. Here if you go for T2 and T graph, T is also here. Okay, integral dt T. I forgot to write T here. Now correct. Okay. Integral dt, K by ms is constant, integral dt will be T. Okay, T also there. So T2 and T graph, if you plot T2 or T2 minus T1 on y-axis and T on x-axis, you get a graph showing exponential decay, and that is called cooling curve. Cooling curve of Newton. Cooling curve. Cooling curve shows an exponential disintegration, exponential decay. Now, log T2 minus 1 and T on y-axis. Log T2 minus T1 on y-axis, T on x-axis. You get a straight line with negative slope. Okay, whose slope is given by K by ms. Here its slope, straight line graph slope is equal to minus K by ms. So m into s is called heat capacity. More the heat capacity, less is the slope. So if material having greater heat capacity will have smaller slope. Material having smaller heat capacity will have greater slope. Okay. Here, different types of questions are asked. For example, the formula, let me write once again, minus dq by dt. Writing left hand side, minus ms dt2 by dt equal to K into T2 minus T1. For example, a hot body cools from some temperature, say 90 degree to 80 degrees Celsius in some time, 1 minute. Then the same body cools from 50 to 40 degrees Celsius in what time? Similar type of questions can be calculated by using this equation. So this equation is to be noted. Very important one. So here basic laws in radiation are Stefan's law, Wien's law, and Newton's law. Newton's law can be only used when there is a very small temperature difference between hot body and surroundings. Okay, it should not be few thousand Kelvin, 500 Kelvin, it cannot be. Large difference in temperatures, 500 Kelvin, 2000 Kelvin, 6000 Kelvin, like that, you can only use Stefan's law. Okay, with that we have finished the quick revision of the chapter. Thermal properties will be meeting with the next chapter, thermodynamics. Thank you.